Yeah, so thanks for having me. Super excited to get to talk to everyone today. And yeah, today I'll be talking about this recent work on conformal prediction with conditional guarantees. And this is joint work with John Cherian, who's another PhD student at Stanford, and Emmanuel Candace. Okay, so my understanding is Anastasios talked a little bit about conformal in this group last week. So hopefully I don't repeat too much information that everyone already has top of mind. Yeah, but very broadly, I'm sort of interested in these questions of we have all these black box models that are performing very, very well in practice, but we don't really understand exactly how they work. And we have very little theory for sort of guaranteeing their performance. Okay, and so in lieu of a complete understanding of what these models are exactly doing, how can we still sort of guarantee that they're trustworthy and robust and perform the way that we want them to? Okay, so in the typical conformal spirit, today I'll be looking at constructing prediction sets. So given some training data xi, yi, coming iid for some distribution p, I'm going to want a prediction interval, which in general I call c hat of xn plus 1, the new test covariance, that's guaranteed to cover my new target y. And throughout this talk today, I'm going to focus on a pretty demanding set of criteria for C. So in particular, as with all conformal methods, I'm going to want C to be distribution free. Distribution-free, I'm going to want it to be capable of utilizing a black box model. So I want to be able to somehow leverage the outputs of my neural network. And finally, I'm going to be even more demanding. I really want C to be conditionally valid. So I want this guarantee that the probability that my target is in my set, conditional on the covariate values, is equal to my target level that I specify of 1 minus alpha. Okay, it turns out that these three criteria put together are actually much too demanding. And there's this nice result from Vogt from 2012 that says that if you have a prediction set that satisfies all of these criteria, then your prediction set must essentially be vacuous. So you basically just have to output, the entire real line. Okay, so I guess last week maybe Anastasios talked a little bit about what do people actually do in this problem, since they can't do full conditional coverage. So hopefully this maybe looks a little familiar. If not, I'll give some details a little bit later on. But yeah, so typically you can't do full conditional coverage. What do people do? They do something like split conformal prediction. And I'll just recall briefly what this looks like. So I start off with some black box machine learning model, and then I go compute what we generally call a conformity score, which I will define a little more detail slightly later on. But for now, you can just think of, I go and I look at the errors of my black box model on a holdout set, and then I run some sort of conformal calibration procedure. And what this guarantees at the end of the day is that the probability that y is in my prediction set is equal to 1 minus alpha, not conditional on the covariates, but marginal over the new draw of the xn plus 1s. Okay, so I started off with wanting exact conditional coverage given x. What I can usually get from most existing methods is this marginal guarantee that where the test covariates don't show up at all. And what I want to talk to you about today is how do we relax somewhere in the middle of these two things. Okay, so I can't get exact conditional coverage. So how do I sort of relax in the middle? Here's one pitch for relaxing in the middle that's been explored. So there's this result from Reno Barber and co-authors. They look at having a prediction set that satisfies that the probability that y is in the set, given that x falls in some set A, should be at least 1 minus alpha for all sets A, such that probability x in A is at least lower bounded by some small amount. Okay, and if you do this, what they show is that even this, I don't know if you see this as a mild restriction or hard restriction. I guess it's up to interpretation. But even this type of restriction is not good enough in the sense that, if you have a prediction set that satisfies this, then its probability of coverage must be at least 1 minus alpha delta. Okay, so for example, if you just consider like half spaces, so you split up X into halves, then your prediction set must be, twice as conservative as you'd like it to be. Okay, so exact and different conditional coverage is impossible. Some people have explored some relaxations, but these relaxations still tend to be relatively conservative. So what am I going to tell you about today? Say I'm going to talk to you about a sort of modification of split conformal inference. I start with my black box model. I'm going to compute some conformity scores, and then I'm going to give you a new, what I call conditional validity method or conditional calibration method that's going to guarantee a much more exact guarantee, much tighter to 1 minus alpha. Okay, and the big idea, I guess, or the big thing that's going to drive this is a new idea of what do I mean when I say conditional validity, a new sort of relaxation of this conditional coverage objective. Okay, so here's how I'll motivate the conditional coverage objective that I will consider. Okay, so I have the following sort of spectrum. On the one hand, I have exact conditional coverage, which was my goal that I stated sort of on the first or second slide. I want probability Y is in my set given X to be exactly 1 minus alpha. And then on sort of the other end of the spectrum, you have marginal coverage, where I just completely remove this conditioning on X. And to motivate what I'm going to talk to you about today, I'm going to rewrite both of these definitions slightly. So first, I'm going to rewrite the conditional coverage objective. So, okay, this is a bit of a measure theoretic definition, but if you open, any measure theoretic probability book, what you'll find is that, this sort of conditional guarantee is equivalent to saying that this expected value of your indicator of coverage minus your target level should be 0, should have the correct mean when you reweight by any function x of the covariates. I'm just realizing there's a typo on my slide, so this x should be the same as this x, of course. So you reweight by the new covariates. Okay, and similarly, marginal coverage can also sort of be written in this variational form. So for marginal coverage, I want the probability that Y is in the set to be 1 minus alpha. And this is equivalent to saying that this expectation of the indicator minus my target should be 0 when I reweight by any constant function. Just sort of, well. Okay, so what am I going to do today? Okay, today I'm going to do something I think seems fairly natural once you look at these two definitions. I'm going to also consider reweightings by some function f, but instead of considering all measurable functions or just constant reweightings, I'm going to ask that my coverage has the correct expectation when I reweight by all f in some sort of restricted function class math call f. Okay, and I'll sort of give some different specifications for what this function class can be and what is sort of tractable as we go along. Okay, I think this definition can be a little bit strange the first time you look at it. Like, what is f? What is this really giving me? So a good sort of example to motivate and keep in your mind as we talk about the methods is if you take calligraphic f to be this class of sort of linear combinations of indicator functions that x falls in some subgroup G for G in some large collection of groups that I'm interested in. So you can think of maybe I'm making predictions for people and I have subgroups, given by like race and sex and age and things like that. Then my this sort of target objective that I've written up here in this context is equivalent to saying that the probability that my prediction set covers conditional on x falling in any of my subgroups should be my target level of 1 minus alpha. Okay, so that's sort of the goal. Now I'm of course going to tell you a little bit about how we get there. And yeah, as I said sort of earlier on, the methods I'm going to tell you about sort of build upon split conformal. So the first thing I'd like to do is sort of give a very quick refresher for what split conformal looks like in the details. Okay. So in split conformal, I start off with some prediction rule F. This is supposed to be like my neural net, my random forest, my black box model that I have. And then I take some calibration set, xi, yi, that are critically different from the data that were used to fit F. So F was fit using some data, a long time ago, and now I have just some new, fresh IID data set. Okay. And then I define what I call a conformity score S. And S is supposed to measure how well Y conforms with the prediction of the model at X. So a good example to sort of have in your mind is that your conformity score could just be the absolute residuals between Y and the prediction of your model. Okay, and then what I do is I go and I compute the conformity scores on my calibration data. So I look and I see, what do the errors of the model look like on these first endpoints. Okay, and based on this, I want to figure out, well, I look at the error on these n IID points. How big should the error be on my new test point? And a good approximation for how big the error should be on the new test point is to just take the empirical distribution of those conformity scores that you just computed, take the 1 minus quantile or 1 minus alpha quantile of that, and say, oh, well, a good upper bound for the new error on the new test point is to say that the new error should be below the 1 minus alpha quantile of the empirical distribution of these sort of previously observed errors. Okay, so at the end of the day, my split conformal prediction set is just the set of values Y such that the error of the model or the conformity score evaluated at Y falls below this quantile. There's one slightly weird thing going on here, maybe, which is that instead of taking the 1 minus alpha quantile, I take this little tweak where I multiply by n plus 1 over n, basically. This just to make the math really clean in the theorem statements, not really an important sort of discrepancy. Okay, so this is how split conformal looks. There's lots of work that looks to build upon split conformal to go past marginal coverage and try to get some sort of conditional guarantees. Okay, so here's sort of a path taken by many papers. So I have some model consisting of my predictions F and my conformity score S. And one way to try to get good conditional coverage is to try to really set up my conformity score to be adaptive to the distribution of Y given X. Okay, so what does that sort of mean? So some examples that have been considered in prior papers is I take like my conformity score to be the absolute residual, but then maybe I normalize by some estimate of the conditional variance of Y given X. Or there's this conformalized quantile regression method that goes and says, oh, let's define this estimate Q hat of like the conditional quantiles of Y given X and build a conformity score using that. Okay, and many of these methods, work quite well in practice, but the theoretical guarantees are quite loose. In particular, in general, if X is some p-dimensional covariates, then under some smoothness assumptions for Y given X, these methods tend to give you a guarantee of the form that the conditional coverage of Y being in your set minus your target level is upper bounded by something that looks like n to the 1 over p, where p is my dimension. Okay, so as soon as p is really bigger than like, I don't know, 3 or 4, this guarantee becomes really quite loose, and it's hard to say anything super precise about what's actually happening with conditional coverage in practice. Okay, so that's sort of the story of past methods. So now I'd like to tell you a little bit about what we do instead. And to start doing that, the first thing that I'm going to do is that I'm going to give you a slightly different description of split conformal prediction that I will build on a little more naturally for the methods that come next. Okay, so here's a sort of different way to see split conformal. Okay, So in split conformal, I want to use the 1 minus alpha quantile of my previously observed conformity scores to make my cutoff for my prediction set. And one way to describe that 1 minus alpha quantile, or to get that 1 minus alpha quantile, is by running a regression. In particular, if I have this pinball loss, L alpha, I have it plotted up here in the corner. It has two slopes. You get slope 1 minus alpha, the bigger slope. If you're an uncovered point, you get slope alpha if you're a covered point. Then sort of the cutoff of the split conformal set is this value Q star. That is results from fitting the quantile with this loss function. Okay, so one way that you can write the split conformal prediction set is that the split conformal prediction set is the set of values y such that the conformity score evaluated with the covariates at the value y is less than or equal to this fitted quantile with this loss function, where I do one thing that's like a little bit weird. So over here, I just have all my observed conformity scores that I saw on my calibration data. And then I make this extra little tweak where I include the test point y, for which I'm trying to sort of evaluate membership in the set, in the fitting procedure. Okay, this is sort of a weird tweak, but I will show why it ends up being somewhat important as we move along. And actually, it ends up being quite critical. So in the split conformal case, it's not super important, but as we move to the more complicated methods, this extra tweak where I include the fitted point is going to be quite important. So I want to emphasize it now. Okay, this is maybe a lot of material. So, and this really what I just said will form the basis of sort of what I do next and what I do for the rest of the talk. So maybe this is a good point to pause and make sure, see if there are any questions and make sure we're sort of all on the same page with what I've said so far.
Yeah, I think one question is about the new notion of conditional coverage, and then how it connects to this new way to define the conformity score calculation. Mm-hmm. So is the intuition behind this new notion is that conditional coverage implies robustness to any distribution shift? Like, is this?
This is true. Yeah, or any covariate shift, you mean, I assume?
Yeah.
Yeah.
So that's the reason. That's the intuition behind this new notion of coverage. So you can really operationalize this notion of coverage for problems where you have covariate shift, because it's kind of like the nice thing about the Brina-Barber's paper with like having coverage hold over any Euclidean ball with probability mass delta is that it's kind of interpretable. So you kind of have coverage over neighborhoods. Mm-hmm. But like how to interpret this new notion of coverage where you have like robustness to a function class of shifts? Like how can you when you apply this method, like how can you think about this new notion of coverage? What does it look like in a downstream application?
Yeah, for sure. So I guess I think about it two ways. So one way is in some applications I have shifts maybe that I am most concerned about or like most interested in. So like a typical setting would be like a fairness setting where I want to make sure my prediction sets perform well over like protected subgroups. And in that case, like I can encode that in my function class and then make sure that I'm guaranteeing that. Okay. If you're in a more agnostic setting where you don't really know what covariates are important, or you don't really know what covariate shifts you think are like the most critical, then what you can do is you can take the function class to be something generic, like something pretty flexible. So well, we're not super close to this, but at some point in this talk, I will state a result for like what happens if I take the function class to be a reproducing kernel Hilbert space, which can be pretty universal, pretty flexible. And then I'll show you how the coverage guarantees behave under that, and you can sort of learn something about your problem. So in Rena's case, yeah, maybe I shouldn't preview too much, but it'll be like maybe a little bit more of a precise, refined version of what Rena has in her case for small sets.
Yeah. And like, how does like maybe you will get into this, but like, I still don't see the connection between this quantile regression definition of conformal prediction and like the notion of coverage, or is this like coming in the later slide?
This will be in like the next 3 or 4 slides,
Yeah.
so maybe I'll just we can
Yeah.
just hold that. Cool. Yeah, okay. In fact, I think the next slide, the next slide is the proof of why split conformal should work based on this quantile interpretation. So maybe that will sort of immediately provide some clarity. So I think this basically answers your question. So let's maybe get into it. So I want to prove that split conformal works. Okay. And in particular, when I've rewritten split conformal as this sort of like quantile fitting procedure. Okay. So what am I going to do? I'm going to look at the KKT conditions, or the first order conditions of the quantile regression fit. Okay. My quantile regression, we'll recall, it's this loss. It has 2 slopes, a big slope and a small slope. And then it has a sort of, it looks like the absolute value function. So it has sort of a sharp kink at 0. So when I look at the first order conditions, what do I have? I have, for all the points that are not at the kink, so for all the points that are not sort of interpolated by the fit, I have one of the 2 slopes. I either get the slope alpha for the covered points, and then for the uncovered points, so the points where the score is above the quantile fit, I get the bigger slope, the alpha -1 slope. And then for all the points that are at the kink, I get some subderivative of the loss, so some value lambda I, such that lambda I is between the two slope values. Okay, and if I rearrange this a little bit, I can rewrite this as, if I look at the average over all the points of alpha minus this coverage indicator, plus there's some optimal variables lambda I star that would give me exact derivatives, or the exact subdifferentials that would give me 0. So I have these 2 terms, one term for the interpolation points, one term for all my points. And critically, when I look at these subdifferentials, they have to lie in this range, alpha -1 to alpha, which means that this second term has some sort of immediate bounds. In particular, this has to be at least -1 and at most 0. And if I rewrite this again using those bounds, I can get that this sort of difference between my target miscoverage and the sort of indicator of the miscoverage is lower bounded by 0 and upper bounded by the number of interpolated points, the number of points that fall at this kink, this point of non-differentiability. Okay. And then sort of the magic step, if you will, is that if I take expectations through this equation, and in particular, if I take expectations over this middle term, what does this look like? So I have 2 terms. I have this alpha term, which I have for all the points. So that just gives me an alpha here. And then I have this indicator of miscoverage. And the really critical observation that's going to drive what I do in this talk is that you'll recall I did this like slightly strange thing where I fit the quantile using the test point in the quantile fit. Maybe it's good to emphasize that. So like in this quantile fit, I have all of the training data, and I have this like test point where I didn't know the test Y, so I've sort of like gone and imputed it in. Okay, and because of that, each of these indicators for SI being greater than Q star have the exact same distribution. So it doesn't matter which I I'm looking at, if I'm looking for one of the test points or one of the training points, it's all sort of the same. And so these indicators just become this probability that SM plus 1 is bigger than Q star. or equivalently, they become the probability that y is not in my prediction set. Okay, and if you put this all together, so here I just have my split conformal prediction set written again. And then if I put this all together, what do I get? I get that the split conformal coverage guarantee can be rewritten as, probability that y is in the set has to be lower bounded by exactly what I want, and then upper bounded by the same thing, exactly what I want. Plus, I pick up some sort of error that has to do with how many points are interpolated in the regression, how many points fall at the kink. And if I assume that the conformity score distribution is continuous, then, for example, you can upper bound this by 1 over n plus 1. Okay. Does that sort of answer the question about at least where the baseline sort of connection is? Or
yeah, I can see it now. Thanks.
Cool. Okay, so that's sort of how split conformal works. And then the next thing I'm going to do is I'm going to discuss, how do I modify this procedure to meet this sort of coverage guarantee under shifts. So yeah, my goal, as we'll recall, was to guarantee that this, expected value of my coverage minus my target level was the correct thing. But when as Alma just rephrased in terms of covariate shifts, so you can think of f being a covariate shift, but really, f can be both positive and negative. So just over some reweighting function, f in my function class. Okay. For the first couple results that I give, it'll be easiest if I allow this function class to just be some like finite dimensional linear functions, though, as I said, I will expand that to some more complicated spaces shortly. Okay, so what's my new procedure going to be? I'm going to make one little sort of tweak to this split conformal setup. In particular, in split conformal, I fit just a single scalar sort of quantile regression fit. Okay, and now I'm going to do something a little bit more complicated. In particular, instead of fitting a scalar value, I'm going to fit a function in my function class. I'm going to run quantile regression using my function class f. So everywhere I had the scalar before, I'm just going to swap in some function in my function class. And then just like before, my prediction set is going to be the set of values y, such that the conformity score evaluated xn plus 1 and y is less than or equal to my fitted quantile function. But once again, I have this sort of weird thing where, because I don't know the test store, because I don't know the true value of the conformity score at yn plus 1, I'm going to impute what I call fs for the last conformity score. So fs is the quantile regression when I fit with sort of an imputed value for the missing score s. And then when I construct my prediction set, it's the set of values y, such that the conformity score evaluated xn plus 1 and y is less than the fit when you use that imputed value. Okay. Okay. And if you do this and you sort of follow a very similar argument to what I just gave on the previous slide, what you can now show is that for all functions in your function class, this method will guarantee that this reweighted expectation of the coverage is always upper bounded by the number of interpolated points in the quantile regression fit. Yeah. Okay. As I said before, I think general function classes, it can be slightly opaque what exactly this method is guaranteeing you. So a more concrete example that you can always have in mind is what happens for subgroups. So if f, again, is my linear collection of sort of subgroup indicator functions, then just sort of following through what I just said, you can guarantee that your coverage conditional on x falling in any one of your groups is lower bounded by 1 minus alpha and upper bounded by 1 minus alpha plus this small correction. So in this case, you can bound the number of interpolated points by the number of groups that you fit over the sample size, basically. So as long as you don't fit too many groups, you'll get basically exact coverage or almost exact coverage. Yeah, okay. And the proof for why this works, so I wrote 3 lines of math here, so maybe it looks a little complicated, but it's actually quite straightforward, or at least, as straightforward as the proof we saw a few slides ago. So I basically do the exact same thing as the proof we saw before. The only difference now is that in all my sort of KKT conditions and all my derivatives that I take, I'll pick up an extra indicator for the subgroup. So yeah, so when I do the subgradient thing, my regression, if you will, has a covariate for every, or sorry, my regression has a coefficient, an unknown parameter for every single one of my subgroups. And if I look at the derivative in that subgroup, that will pick me up some sort of indicator function. And then if I carry this through as before, so, I have my KKT condition, 0 has to be, somewhere in this set of subdifferentials. I do the same thing I did before, where I just do some algebra to rearrange this slightly in terms of the, optimal subdifferentials that give 0. This term can be bounded because lambda I has to lie in some bounded range. And then just as before, I just take an expectation over my first order condition, and that makes it so that, this sort of coverage indicator becomes my, probability of coverage given that xn plus 1's in the group. Okay, so really nothing going on here that's different than the math we saw a couple slides ago. All I've done is just add a group indicator everywhere. I think this is sort of the main thrust of the methods I'll be showing you. So this would be another good time maybe to pause for questions and see if we sort of are clear on what's going on.
So are you making a restriction on the function class you're using here? Is it like, does it have to be finite dimensional, or is this like the general, like the same proof? Or
yeah. So the proof will always be similar. I think I'll give an infinite dimensional statement in like a couple slides. The biggest thing in infinite dimensions, but we can preview a little. So if I want to do this fit in infinite dimensions, it doesn't really make sense to do this fit as written in infinite dimensions. So like if I make F very, very flexible, then, and I do exactly this fitting procedure, then F will interpolate the training points. So all the points will be interpolated. And then what happens if all the points are interpolated? Well, if all the points are interpolated, then all my points are sort of at the kink of my fit, and my upper bound will become completely vacuous. So that's no good. Okay, but of course you would never fit an infinite dimensional class like this. You would fit with regularization, and I'll give a statement in a little bit that like says something about what happens when you fit with regularization.
And
So to state this meaningfully and to have this interpolation term not be ridiculously large, I have to restrict myself. Like I have to restrict my dimension a little bit, I guess.
And like, I think for the subgroup example, a comparable approach or like another approach would be binning. So like you can bin the subgroups and just like do split conformal within the subgroup. Yeah. So what would be the trade-off here? Like, are you gaining something by calibrating with respect to this like linear class?
Yeah, for sure. Yeah, for sure. So if all the subgroups are disjoint, this will be equivalent to binning because nothing will influence each other, and you'll just end up fitting you'll fit the quantiles in every bin, which is exactly the same as what you would do in split conformal. If the subgroups are overlapping, then your fit will share some information across the groups, and I guess this will generalize what's going on in binning a little bit.
Okay.
Yeah. Cool. Okay, so here's an example of what this looks like in practice. So I just take my set of subgroups to be these intervals AB, where AB lie in this range. So critically here, I can have overlap, like the 0, I don't know, whatever. The 0, 1 interval overlaps the 0.5 to 1.5 interval. Okay, and I run two methods. So in blue, I have split conformal. Split conformal, it starts off with some curve fit. So I have some black line that I fit. That's supposed to be my black box model. Okay, here my black box model is just some sort of, polynomial regression. And then what split conformal would typically do is it would give you some constant width bands around this fit to be your prediction set across the line. okay, if I run the method I just described to you with these subgroups, then I'll get some sort of more adaptive fit that looks like some sort of step function corresponding to the fact that I fit with these sort of discrete groups. And if I go and I evaluate the coverage, then we see that this method I just showed you in orange gives sort of exact coverage under multiple scenarios. So it gives you exact marginal coverage, so exact coverage over the whole real line, where split conformal also guarantees you that. But then if you look at coverage in subgroups, so for example, the subgroups corresponding to these gray bands, then this orange method will also give you exact coverage there, where split conformal can give some sort of variable performance. Okay. As maybe was alluded to earlier, you can also sort of reframe a lot of what's going on here as coverage under covariate shift. So what do I mean formally by this? So by covariate shift, we generally refer to the setting where my training data come IID from some distribution P, and then my test point comes from the distribution QX times PY given X. So in particular, the distribution of Y given X is the same, hasn't changed, but then X is drawn from some new distribution QX, where for us in this talk, I guess QX will be formed by tilting PX by some function. So I take my original sort of distribution P and I reweight it by some function of the covariates. Okay, and then asking for coverage under covariate shift is the same as saying, okay, suppose my data follow this sort of format, then what I want is that I want the probability that Y is in my set to be my target level 1 minus alpha under what I call PF, or P subscript F, to denote the fact that my covariates have been reweighted by this function F. Okay. And yeah, so our method is the method I just described to you is sort of exactly set up to sort of handle this situation. So for example, if F is some linear functions where the features of my linear functions are positive, they have to be positive because if I want to reweight a probability distribution, I need a positive function there. And again, I make some continuity assumption just to control the number of interpolating points. Then my probability of covering under covariate shift, so my probability of covering under the shift by F is guaranteed to fall between 1 minus alpha and 1 minus alpha plus this dimension over the sample size. Okay, where here F, the functions I consider have to be, of course, functions that belong to my set of shifts that I sort of pre-specify. Okay, again, just like a look at what this looks like in practice. So here I take my function class to be sort of some linear functions over, well, I have an intercept term, and then I have some sort of local reweightings of the data. So in particular, I take some Gaussian kernel centered at different points xi. I look to sort of locally reweight the data around those points. Here I have split conformal. It gets me these sort of constant width bands as before. Here we have our method. In this setting, our method's maybe a little spiky in this example. So it goes, if you look at my gray dotted lines here are two of these sort of kernel reweightings. And our method is supposed to be lined up to sort of adapt to these kernel reweightings. So it has some maybe sharp behavior around the kernel functions to get the fit right there. And indeed, if you look at the coverage, the marginal coverage is correct for both methods. And then for each of these two sort of local Gaussian reweightings, split conformal, which is in blue again, can get sort of variable performance. But okay, the new method I just described to you gives sort of exact performance everywhere. Okay. Yeah, so that's sort of all the finite dimensional results. I do want to discuss this sort of infinite dimensional extension. So as I said earlier, I think in some settings, you might have a pretty good idea of the covariate shifts that you care about. You care about fairness, guarantees. So you want coverage under, some protected subgroups, or maybe you have some features that you think are particularly important and you can sort of encode those in a a model. In other settings, maybe you don't know what covariate shifts you care about, and so you'd like to do something more flexible. So here's sort of an answer for how you do that. So suppose F is an infinite dimensional vector space, then the natural sort of extension of the method I showed you earlier is you fit the exact same thing as before. You fit a quantile regression using your function class F. But now, as I said before, because it's infinite dimensional, you're going to have to do some sort of regularization to get like a reasonable fit out of this procedure. Okay. The other comment that I'll make, just to preview what I'm about to say next, is that you know that you cannot get exact coverage of over an infinite dimensional class. So, in particular, like if F is like the infinite dimensional class of all measurable functions or some other, sorry, just give me 1 second. If F is if F is the infinite dimensional class of all measurable functions or some other very flexible class, like some very large kernel class, I sort of said at the beginning of the talk, you can't expect to get exact coverage under all of these functions. Okay, so you know that that's impossible from the get-go. So what are you going to get here instead? Okay, you're going to get something that looks like this. So here I've stated the result in terms of covariate shifts. So suppose I take a non-negative function in my function class, then what's my coverage guarantee? My guarantee will be that my covariate shifted coverage is bounded between my target level, and then I'm going to have this sort of offset term. And this offset term will scale with, well, it'll scale with how much does F align with sort of the bulk of the X distribution. And then the real sort of, the real size of the offset will really be driven by my penalty function. So in particular, we recall that sort of all my coverage guarantees are driven by first order conditions. So what shows up now is exactly sort of a first order condition for the penalty. So in particular, my coverage gap will scale like the derivative of the penalty function at, this is my fitted quantile function. My fitted value of my quantile regression. And then I have to perturb that in this direction, F, where F is exactly the thing that I'm evaluating coverage over. So F shows up. The thing I evaluate coverage over shows up sort of in both places. And then this is my fitted quantile regression function. Okay. And then I also have sort of a matching upper bound. So my coverage is also guaranteed to be upper bounded by the sort of exact same thing, except I pick up this extra term that we've had this entire time, which is my interpolating points. Okay. Okay, I think the previous statement is like, well, maybe a little bit much to parse. I don't know if this will maybe be slightly easier to parse and a little bit more of a concrete example. So suppose I take F to be a reproducing kernel Hilbert space, and I take my penalty function to be the squared norm, the squared kernel norm. Then what do I get? I get that my coverage is lower bounded by what I want. And then this offset term, this derivative of the penalty function, becomes just a simple inner product between the covariate shift that I'm evaluating and the quantile fit. And then again, I have a matching upper bound, exactly what I want, the same offset term. And then in this kernel setting, you can control the number of interpolated points. So you can show that the number of interpolated points scales like 1 over the penalty parameter times n. Okay. Yeah, there's one thing I really want to highlight here. So I think I said before that I think this result is a little more adaptive than the Barber result. And the reason I think it's a little more adaptive is that it scales with the covariate shift that you're evaluating. So if I want to know what's happening to the covariate shift F, then I have a sort of exact coverage gap that scales exactly with the covariate shift F that you're sort of looking at. And I claim that this sort of intuitively makes sense. Like just if you think about, some data in your mind, it's sort of hopefully reasonably intuitively obvious that like some covariate shifts affect coverage more than others. Some covariate shifts are sort of orthogonal to the shape of the variance of the data. They like don't really correlate with anything important, and so they don't really matter for affecting coverage. And some covariate shifts matter a lot. Sometimes you consider a covariate shift that moves you from like all the low variance points to all the high variance points, or something very extreme. And there coverage can be very difficult, and you expect to see some like big changes. And what I like about this bound in comparison to the Barber bound or like some other results is that it scales with the covariate shift that you're sort of evaluating on. Okay. Yes. And then the other thing to really emphasize is, okay, it scales with the covariate shift I'm evaluating on, and it scales with the covariate shift that I'm evaluating on in a way that I can actually sort of quantify. So the result I have in the previous slide shows that my coverage is like 1 minus alpha plus this, expectation. And critically, this sort of offset, this sort of discrepancy in the coverage is an estimatable quantity. So for example, for the kernel function classes, if I restrict myself to functions that have some reasonable density, some reasonable sort of lie reasonably in the bulk of x, or give some reasonable weight to the bulk of x, and I let f hat n be some like fitted quantile regression on my observed points, then this gap that I want, I can estimate it just using sort of an empirical plug-in estimator up to some sort of reasonable accuracy. Okay. Yeah, okay, so that's sort of the deal for infinite dimensional functions, or that was most of what I want to say about infinite dimensional functions. I have an example of what this looks like sort of in practice next that will hopefully really make this clear, but any questions about sort of the math before I move on?
So is it correct that if I want to interpret this guarantee as opposed to Barber's paper, this is more like if you want to localize this notion of coverage, it's not over all Euclidean balls for any test point that have mass delta, it's like over kernels. So like if you want to interpret this in an actual, like if you're using a model that has this guarantee and you want to reason about the coverage it's giving you for individual predictions, so is the interpretation that for a distribution localized around this new test point with these kernel properties, you have the guarantee holding, or like, is it not straightforward to actually translate this guarantee into a conditional notion of coverage? You see what I'm
Yeah, I do. So let me say something. You can tell me if this clarifies. So in arena sense, I can consider all balls. So let's consider something that's sort of like balls. Suppose I take a Gaussian kernel. It's like pretty similar. I'm looking at some local thing, like in a ball around a point. Okay, so I take a Gaussian kernel. I look at a point, or the Gaussian kernel reweighted around, a point, and I ask for the local coverage there. Then really, similar to the arena paper, I'm also giving you some coverage guarantee about what's going on locally. The difference is really that in their case, their coverage guarantee is lined up to be sort of universal, and because it's universal, it ends up being a little bit loose. So it sort of gives like the same coverage guarantee for every ball.
Oh, I
but
see.
all balls are really the same. Like some local reweightings, give you big over coverage. Some local reweightings will give you big under coverage. Some local reweightings don't matter. Some local reweightings are sort of like neutral. And the real difference I've seen between what we give and what they give is that their guarantee is sort of completely agnostic to which local reweighting you're looking at. Whereas for us, we can quantify what's going on at every single like local reweighting you want to query.
I see.
Yeah.
And is there a reason why you would pick like one function class over the other? Because it seems RKHS is very convenient and still like independent from the actual model that you have fitted to make the point predictions in the first place. So it's still model agnostic in that sense. Is there any reason why you would think about using looking into other function classes where maybe the regularizer wouldn't be tractable, or like we wouldn't actually know what's a good regularization term?
Yeah. So the math is, RKHSs are popular for a reason. It's because the math, they're a lot easier to do math for than lots of other function classes. And that also sort of holds true here to some extent. So to do the math here, I have to do things like, control how I can estimate what's going on with the regularizer. So this is really like some estimation that's what's going on with the regularizer. And I have to do some math about like controlling the number of interpolated points in the regression, which turns out to be not like super trivial. And for this, RKHSs are convenient. From a practical perspective, like, is that a reason you should use an RKHS as opposed to something else? Like, not really. But I don't have any, I guess I don't have any great insight for like why, should you choose an RKHS? Should you choose some other flexible function class? Even if you choose an RKHS, like which RKHS should you choose? I guess like, I don't have any great insight other than to say like, you should choose what's convenient for the covariate shift that you intend to evaluate at the end.
Yeah, and just one more like general question, even considering the finite dimensional case, like if you care about a specific notion of coverage, like subgroup level coverage, do you lose anything in terms of efficiency if you use your method? Because I think your guarantees are stronger, right?
Stronger than what? Like than split or something, or than
like for instance, in the subgroup level coverage case, your guarantee is not just giving marginal coverage conditional subgroup, it's like overall linear.
Yeah.
So it's a stronger notion of coverage. Do you lose anything in terms of efficiency compared to binning, for instance?
I think in the subgroups case specifically, linear reweightings over the subgroups and conditional guarantee on the subgroups. Like I think conditional guarantee on all the subgroups certainly implies coverage on conditional reweighting. So I think in that case they're actually not stronger. I think those are two things are identical. In the general case, I guess the question is like it becomes a little more complicated. I don't have a perfectly clear answer. One thing that I do think is important is like when we talk about efficiency, I guess we're talking about like set size or something like that. Which is so my one thing about set size is you have to say losing efficiency relative to what. So one thing you guys just like, are your sets bigger or smaller than the split conformal sets? And that question I actually think is like not quite the right question. Why do I think it's not quite the right question? Well, our coverage guarantees are very different than the split conformal coverage guarantees. And here, maybe let's get like this plot. So like, here my interval, like in this region, my interval is a lot wider than the split interval. And in this region, my interval is smaller. But like, is that a good thing or a bad thing? Well, I guess I would argue to you that it's like the correct thing. It's like what's actually going on with the data. Like I'm just giving you the interval that represents the data. So I think it doesn't make sense to compare efficiency against like a different method with different coverage guarantees. So then the question really becomes, well, do you lose efficiency relative to like some other method with similar coverage guarantees? And I don't actually know what I don't have a good other method with a similar coverage guarantee to compare against. So I can't tell you if I lose efficiency relative to that because I don't know another method that does something similar.
Yeah, I guess the reason I'm asking this is like would this be a good way to pick different for different choices of the function class that you are using for category, like maybe like I'm trying to come up with a trade-off for like you should be losing something and gaining something if you like use one function class or like one regularizer versus the other in the infinite dimensional case or even in finite dimensional case. I'm not sure whether there is such a trade-off, but maybe looking into efficiency might be helpful.
Yeah, I think that's a really I think that's really reasonable, especially in the infinite dimensional case where it becomes like less clear how you should choose between things. I think that sounds at least plausible. But I don't have any specific insights. But I agree that seems reasonable. We are at 3 o'clock. I don't know what your
I think depending on when do you need to hop off the call, but like we are available until 3:30.
Okay. I don't have too much more content, but I wanted to make sure that I wasn't,
you're good.
messing up your schedule.
No.
But yeah, okay. So this example is nothing complicated. So this is just I fit with a Gaussian kernel, and my plots here. So I get some intervals that look like this. Here are two sort of local Gaussian reweightings. And as I said before, the nice thing about our method is I can estimate what actually the real coverage is. So for each of the two reweightings, so the F1 and the F2 reweighting, I can give you an estimate of what the coverage will be when you look at that local reweighting that matches, what you see empirically. So it's just emphasizing sort of the last theorem, I guess, that I showed. Okay, here's a more concrete real data example. So I look at the communities in crime data set. The goal here is to predict the crime rate in a bunch of different like local regions in the US. And as covariates, you have like the age of, or the average median age of like people who live there, their median income, some information about the race distribution, the unemployment information, etc. Okay. And to sort of illustrate what my method does there, I'm going to focus in particular on 4 racial features consisting of the percentage of these 4 different populations. Okay. And then I'm going to fit a function class that has sort of 2 components. It's going to have a kernel component corresponding from the Gaussian kernel. So there's my Gaussian kernel. This is my sort of RKHS component. Okay. And then I'm also going to have a linear component consisting of these 4 racial features plus an intercept. Okay. And my penalty function will be penalization of the Gaussian kernel. So I'm going to penalize, take the, this should be subscript k because this is the kernel norm of fk. Yeah. Okay. And the way to sort of interpret this, and the thing I want to illustrate is that, so I only regularize part of the function fit. And what you can think of this as is like prioritizing certain covariate shifts. So in particular, for my linear shifts, my 4 racial features that I'm giving like priority to, those features will be given no penalty and therefore exact coverage. And then the rest of the features I've sort of taken like an agnostic view of, and those features I have to penalize and they will incur some coverage gap. Okay, so like just verifying that indeed all the intuition does work out. So if I look at my 4 linear features and I look at what happens under linear covariate shifts, then indeed, split conformal can give you variable performance, but my method, which is in orange here, can give you exact performance under sort of all the linear reweightings under these racial shifts. Okay, on the other hand, what happens when you look at the RKHS components? So for my RKHS component, as an example here, I've plotted 2 covariates that were used in the RKHS fit. So here I have the percentage of people in the community that are over the age of 65. Here I have the median income for the community. Okay, the scale has been normalized just to be between 0 and 1 for like convenience. And here I just have some examples of the Gaussian kernel. So, I'm fitting some sort of local reweighting around different points. And what you can do is, so I look at my RKHS fit around different local reweightings, and I can get sort of a heat map like this that evaluates what the coverage of the method will be at all the different points. And you can just sort of, easily from this heat map see that like for older communities, the method will tend to undercover. Okay, so I guess at the most extreme, I'm getting maybe like 80% coverage when I think I'm targeting 90%. And then for younger communities that are maybe have higher median incomes, the method will tend to overcover. So you can sort of evaluate the coverage across, as you vary the features or as you look at different like local aspects of the space, and you can get sort of a coverage estimate that is sort of adaptive to which part of the space you are looking at. Okay, and then the second plot just verifies that the dots on this heat map are accurate, so that in the heat map I'm plotting some empirical estimates, and indeed the empirical estimates match the true realized sort of coverage. Yeah, okay, that's sort of it for the applied example. Maybe I should just pause one more time for questions there.
Okay. Like, so for the like this idea of local reweighting, is it possible to, like, for each new test point, apply localized reweighted conform prediction for that test point, would you get better guarantees in this case for older people, for instance, in this example? Like if you don't, you probably don't need to specify beforehand there's one way to guarantee conditional coverage where you kind of have the guarantee hold for a function class that you determine beforehand. Like, but could there be like another procedure where, given a test point, you kind of try to achieve conditional guarantee, conditional on a distribution localized around this test point, and in this case, you get like better, more uniformly distributed conditional coverage for in the feature space.
For sure.
Such method exists already. I'm not sure.
This method does exist, but it only exists as of 4 weeks ago or something.
Okay.
So Rena Barber has a paper with her student that I think was posted to archive, I don't know, less than a month ago. I can't remember how long ago, that basically does exactly what you're suggesting. You have to be, careful in all the details to make everything work, and they are careful and they have done it. Yeah, so the answer is this is a reasonable method that has been sort of proposed fairly recently. I think the relative trade-off there is the nice thing about using a small pre-specified function class is you can give some very tight coverage guarantees for a small pre-specified function class. If you try to do something very agnostic, as dimension grows, like you're going to have to give up something, basically. So it's just this sort of trade-off between you ask for less, you get something more tight. You ask for more, you end up degrading a bit. Yeah,
I see.
Yeah, but certainly both things are reasonable and have been explored a little bit.
Yeah.
Okay, I had just one more thing that I wanted to say, but I'll keep it very brief because I know we're sort of pushing time a little bit. So I won't even say anything, I think, in technical details. I'll just make a comment that sort of this exists in the paper, and if you're curious, it's there for you. So I define my function class, I define my prediction set as C hat to be this set of values Y such that the conformity score evaluated at Y falls below the fit when Y is used in the fit. And if you're not very careful with things, this should look uncomputable to you. In particular, for every value Y, if I want to evaluate if Y is in the set, then I need to fit some regression that involves Y. So it sounds a priori like I need to fit like infinitely many regressions to compute this prediction set. Okay, but this turns out not at all to be the case. And you can actually do this all exactly. So we have some methods in the paper that actually compute this set very, very efficiently. Yeah, and I think because I'm pushing time, maybe I won't go into it too much, but it's there for you if you want it. Okay, so I'll skip this stuff. Okay, I have one final comment that I want to make. So this is my last slide, which is again, sort of throughout this talk, I've been talking about using the test point in the quantile regression, using this sort of imputed value of Y. And I think it's a fair question to sort of throw it back to me and ask, like, how important is using this sort of imputed value of the test point in the quantile fit? In particular, a sort of alternative procedure that you could consider is what happens if I just run vanilla quantile regression? Suppose I just don't include the test point in the fit, and I just run quantile regression on your n training points. Okay, and this is a plot that sort of addresses that. So in green, I have what happens for vanilla quantile regression. In orange, I have the method I've been talking about to you this whole time. And what you see is that as you raise the dimension of the function class, sort of vanilla quantile regressions can sort of progressively overfit and give decaying coverage. So the coverage, I guess once the dimension is 50 for 250 samples, the coverage is only like 80%. Whereas by doing this sort of tweak where you include the quantile regression or the extra test point in the fit, you can sort of correct for overfitting and maintain sort of exact coverage throughout. Okay, so that's sort of, I think, the big sell for why you include the extra point in the fit. It's because you can sort of correct for overfitting in this very sort of agnostic manner. Okay, that's all I sort of had. We have a paper on archive. as I said, there's an efficient implementation on GitHub.